Morning, sir.
Good morning. How are you? Morning, guys.
Good, sir.
Good, thank you.
Good. Okay, guys. So, uh, do we have any of my DPQ students here? DPQ students, some of them wanted to learn about the integration techniques, and that's why I allowed them to join us. Do we have any DPQ student here? Except Ismail.
Yeah.
I know.
I'm here.
You know, he's a brave boy. He's a brave guy. Yeah, he's taking Calc 2 and DPQ simultaneously. Anyway, guys. So, do you have any problem in the syllabus? Any problem in the syllabus? I mean to say, if you have any doubt, please let me know. Of course, we went over almost everything, but even though if you have some doubt, please let me know. And I'm sorry, I just got busy yesterday, but I'm going to prepare your practice test maybe very soon, at least for Iman some. So I'm going to give you 8-10 examples, something like that. And I will post on Canvas. So I will do it very quickly. Okay, maybe today afternoon or like this, because I'm teaching till 12 and then after my research, today afternoon, maybe I will be doing that thing. Okay, so if you have any doubt, if you want me to solve any of the examples, please don't hesitate. Please go ahead. I give you a couple minutes. If you want to ask me something, go ahead. So first of all, Riemann sum for the partitions, number of partitions in general, n partitions, then n tends to infinity. Then we went over the fundamental theorem of calculus, right? And then we went over fundamental theorem of calculus part 1 and part 2. Part 1 means your upper range is a variable, it's not a fixed real number. And part 2 is in both the parts we have f is continuous in a closed interval a to b, and capital F is the entire derivative, or you can say integration of small f. Then integration a to b fx dx, small fx dx equal to capital Fx is the integration, and range is a to b. So replace your x by upper limit b and then lower limit a. So fb minus fa, in between negative sign. And then after we went over we went over the some techniques of, there's some integration problems, U sub and some like this. And then after numerical integration, so which gives us the approximate value of the area under a curve. We went over two types of things. One is trapezoidal and one is Simpson's. I told you there are two Simpson's rules. One is Simpson's 1/3 rule and 1/3 rule. 1/3 and 1/3, of course, 1/3 is more accurate than 1/3, but 1/3 is not there in our syllabus. So we will just stay with trapezoidal and Simpson's 1/3 rule. And Simpson's rule is more accurate than the trapezoidal. The only thing geometrically in trapezoidal, you have trapezoids. So suppose you have some rectangle. Let me just explain to you in trapezoidal and Simpson's what is the situation. I can show it to you over here, just wait. Look at here, look at the same figure which I took the picture and sent it to you. Look at this. Can you see this one, guys? This one. Can you see this one?
Yeah. Yes, sir.
Yeah. So look at over here. Instead of curvature, I just converted that curvature to straight line above part. So, and you can see this is my first trapezoid. This is the line, this is a straight line and two perpendicular lines. So this is first trapezoid, second trapezoid, third trapezoid. So curvature, if you are making number of partitions, that means curvature is converted. You can consider that curvature just as a straight line, because that curvature in a very small, tiny partition, you are not going to get any kind of curvature. It's just kind of a straight line. But you can't ignore it. Anyway, so that's why, so we are just counting all these trapezoids, and that's why it is called trapezoidal rule. So actually, this is the Rolle's theorem, so I should not write over here. I should have written down over here, trapezoidal rule. So if you have like this, 1, 2, 3, 4, 5, and trapezoids. Look at here, like this. So this one is the trapezoid. So we are just summing up or adding up all these type of trapezoids. That's why it is called trapezoidal rule. While in Simpson's, we are taking care of the curvature, and that's why it is more accurate. That's why it is more accurate. Okay, guys. So you don't have any problem, right? Shall we start the new chapter?
Sir, I have one question.
Go ahead. Go ahead.
Are we gonna have a problem for when it's like when you have to integrate with variables where the fundamental theorem says that it has to be continuous, f of x has to be continuous. Is there ever going to be a problem where the bounds aren't continuous within the interval?
Bounds are continuous within the interval. What you mean? It has to be continuous.
Are you going to give us a problem where it's like not
continuous?
And like, yeah, and ask us.
Oh, no, of course not. I told you yesterday, we are working with Riemann integration. Riemann integration for condition is your function must be continuous. If your function is not continuous, in that case, you cannot find the area. You cannot get the integration. So just forget about it. Yeah, it has to be continuous. F is continuous in a closed interval AB, then whatever integration range is fixed or variable, that works. But without continuity, you cannot think about the integration, Riemann integration. There are some integration that is called Lebesgue integration, but that is not for you guys. It's a higher level mathematics. Those who are math majors and doing masters, graduate level course, and one of the courses that is real analysis. In that analysis, one more integration is that is called Lebesgue integration, in which your function need not be continuous. But here for your course, it has to be continuous. There is no any doubt about it. Right?
Okay,
so
thank you.
Nobody can ask you the example based on non-continuous function. No way. Okay, good. Any other question? Any other question? Okay, guys, so shall we start the new chapter? Yes, for new chapter, everything is well prepared. Look at over here. Yes. Chapter number 6, techniques of integration. Techniques of integration. So several different type of techniques we are going to see in this chapter, right? And I will let you know one by one. This chapter is the most important chapter for you guys. Please keep in mind this thing. STEM majors mainly. You are going to use this thing throughout your life. Throughout your life, yes. If you are engineering major and suppose after your graduation you go for a job in some firm, in some company, and suppose you require to do some kind of calculations, at that time also this chapter will be helpful to you. So this is the important, I would say this is the heart of your course. If you are done with this chapter, that means you are done almost you are done with your DFQ course. Ismail, he knows this thing that I have been using this chapter mainly, techniques of integration, almost in 2 hours, almost 1 hour 30 minutes or 1 hour 45 minutes I'm using DFQ. I'm using Calc 2. So without Calc 2, don't think that you can survive in DFQ. You have to have really good command over this subject, this article, this chapter. And if you are done with this chapter, you are absolutely fine, trust me. And again, let me remind you, after Calc 2, sign up for DFQ. Don't go for Calc 3 or like this. This is just a suggestion. Okay, guys. So first of all, my first example is 3x squared x cubed minus 5 to the power 7 dx. X cubed minus 5 to the power 7 dx. Look at over here. How can I get the integral? When I say this thing, all you guys are requested to focus only on my cursor. Don't look at the things what are given over here, what I have written down below or just side of this page, the example. No, just pay attention on my cursor. So 3x squared x cubed minus 5 to the power 7 dx, right? Now, I want to use over here u sub. Why? Why u sub? Why not any other technique? Now, first thing is, suppose I want to multiply this with this. Is it possible to get the multiplication? No, because here power is 7. You cannot multiply this function with this one. If power is 1, you are good. You can multiply this with this one and you can go for term by term integration. But if power is 2, first of all, you have to expand that quadratic function, right? X cubed minus 5 to the power 2. So a minus b square is a square minus 2 times ab plus b square, and then multiply with this one and go for term by term integration. If it is cube, you know cubic formula a minus b cube. The formula is given also in your formula sheet. It is a cube minus b cube plus 3ab square, 3a square b minus 3ab square. This is the formula. So expand this one and then multiply with this one. If it is 4, now the task is little bit harder for you because you don't know how to expand power 4, 5, 6, 7, 8, 9. You don't know. You can use the binomial expansion, yeah, right? But again, it's very lengthy. One can use binomial expansion and then multiply with this one and you can get the same answer, right? The easiest way is I can use u sub. But U sub for which function? That is the another problem. People are always making mistake choosing your U sub. Sometimes they are using U sub blindly without having any concept, without making sense. Why? Why? Because if you do that thing, out of 10 problems, maybe you can get one example correct, but rest of the 9 examples will be wrong if you are doing math without understanding. So that's why in this chapter, I'm going to give you lots of hints. So please try to pay your full attention. So many times I will be giving you the hints kind of thing which are not given in the books, a trick kind of things. Why is the main major question in mathematics. If you ask to yourself, why I'm doing this thing? Why not this one? Why not this one? And answer and satisfy yourself correctly. Ask to your colleagues, look at the videos, go to online websites and try to find out something. Read the book, discuss in between with your colleagues, discuss with your teacher. But please try to get the answer of all your whys. Why? And that is the best way, or I would say only way to learn mathematics. Why I'm doing this thing? Why not this one? Why not this method? Why not this method? Why this particular method? Yes, that's the best way to get good command over that particular article. So please always keep in mind this thing. Nobody is going to teach you like this. If you go to your class, your teacher will just solve the examples because he has to finish the syllabus. So he will stay with the syllabus and like this, but nobody is going to let you know all these things. So please, these things are more important than this thing because these things are given in the book too. But the things which we discussed, you won't find in the book. Right? So now, main reason of U sub is when I can use U sub. Again, when? Main reason of U sub is U sub reduces your power by 1. Suppose you have x cube. Suppose I have one function. Suppose my U equal to x cube. So what is my derivative of U? With respect to x, U equal to x cube. Where? What is the derivative? U equal to x cube. So derivative of U with respect to x is?
3x squared.
3x squared dx. Right? 3x squared dx. Are you getting me, guys? Now see here, I gave you the function x cube. And he gave me the derivative 3x. What's the power? 3x squared. Your power is reduced by 1. Am I right? Cubic function is converted to quadratic function. Getting me or not? So U sub means always you are looking for one less power associated with your function in the integrand. Now look at over here. And one more thing, again, let me repeat this thing that you can always play with the constant. Yeah, constant doesn't matter. You can always, because constant, you can always pull it out. So it's okay, fine. I don't bother about it. So x cube minus 5 to the power 7. If I consider x cube minus 5 as my U, that means my derivative will be 3x squared dx. Look at here. And I'm having this 3x squared over here. Suppose I'm not having 3x squared, I'm having just x squared. Fine, sounds good. Just x squared is there, divide by 3. You can play with the constant. So du by 3 equal to x squared dx, and you're getting this one. 3x squared is there, that's fine. So let me keep like this 3x squared dx. That means, again, whenever you want to use U sub, make sure that you have to have the another function as a multiplier with power less than your highest power of use, your substitution U. My highest power of x over here for the substitution U is x cubed minus 5. And as a multiplier, I have 3x squared, one less power. Yes, my U sub will work. But suppose here I have simply x, my U sub will not work here. I have to go for some other technique. Suppose I have x cube here. No, my U sub will not work. Getting me? So don't think that whenever I say U sub, that means I'm just using blindly because I don't have any other choice. No. Everything, each and every step, each and every word makes sense in mathematics. This is not the literature, guys, that you can skip one paragraph and you can move ahead. No. So if I consider this as my u, because my derivative is 3x square dx, 3x square dx, so 3x square here, this circle, and this circle is dx, that is my du. So let me write du here. And this was my u, so u to the power 7, u to the power 7, that means I'm getting this one. Once you have this one, just go back to your first chapter, power rule. What was power rule? X to the power n, look at here, x to the power n is n x to the power n minus 1, agree? Actually, whatever the power rule you guys were taught, that is the incomplete teaching. I'm sorry, but that's the fact. I would always look at the power rule in this way. D by dx of x to the power n. That means power means, let me consider that power as a coefficient. So n, then x as it is my variable, and x to the power n minus 1. Agree? Reduce the power by 1, that is power rule. But then we forget at that time to take the derivative of x. Derivative of x. Of course, derivative of x with respect to x is just 1. So that's why people don't explain this thing. People don't write. But if you think like this, you won't make the mistake if your function is different. Different, I mean to say, look at here. D by dx of sine cube x. Now I don't have x cube. I have sine cube x. Trig function and power. That means I can write d by dx of sine x and whole cube. Agree? Sine x and whole cube. Now if you look at like me for your power rule, what are you going to get? You are going to get like this. Look at here. First of all, power as a coefficient. So 3. This is my function. I can't change my function whenever I'm using power rule. Please. People are doing this mistake. They take the power rule and they take the derivative simultaneously. That's wrong. Derivative must appear separately as a multiplier. So first of all, this is just my function. You can say u. Don't change it. Just take care of your power. So 3 times sine x power 3 minus 1 is 2 and minus 1. And then d by dx of x. X is this function. My function is here sine x. So d by dx of sine x. And derivative of sine x is cosine x. So my value, my derivative will be 3. My derivative will be 3 cosine x and sine square x. See, or 3 sine square x and cosine square x. So actually I'm using over here chain rule. So make sure whenever you are using power rule at that time, it is not simply a power rule, chain rule is included. Because derivative of x with respect to x is 1 and that's why we neglect it. But in my personal opinion, that is not it should not be neglected. Otherwise, you will be getting confused if you have this type of function. So always think like this. Whenever you have power rule, just merge your power rule with your chain rule. That is the best. I don't know how you guys were treated in your Calc 1 and I don't want to know. That's not my job, please. I don't want to criticize anybody. No. Everyone has different technique, different way of teaching. That's fine. Are you getting me, guys? Right? So always look at the power rule like this. So here, suppose why chain rule? Because if I consider this sine x equal to suppose u, sine x equal to u, right? So sine x equal to u, that means I'm getting u cube. Agree? And du equal to cosine x dx. Am I right? Du equal to cosine x dx. Now, dx equal to sine x is u and cube. I cannot take the derivative of u. Am I right? Derivative of u with respect to x. How can I take this one? If I want to take the derivative of some function with respect to x, I have to have my variable x over here. But I don't have any x here. I have u. That means I am using chain rule. That means I am using chain rule. Look at here. Chain rule is replace this x by u and then du by dx. So I'm multiplying and dividing by du. Look at here. So d by du of u cube, so that now I can take the derivative of this function u cube with respect to u and du by dx. Then separately derivative of this inner function. Chain rule, that means you have to take the derivative from the most outer side and try to come slowly to the inner functions. Inner functions like this. Just take the derivative most. Suppose I give you one example of suppose sine x over x cube. Sine x divided by x cube to the power 5. So first use the most outer side. 5 as a coefficient, sin x over x cubed to the power 4, and then use the quotient rule, your calc one, quotient rule, sin x over x cubed, quotient rule separately as a multiplier, side to your power rule. Are you getting me? Means we are using chain rule. So u cube is 3x, 3u square derivative, and du by dx, u was sin x, so naturally du by dx is cosine x dx, or cosine x, du by dx is cosine x, just divide by dx. So cosine x, and I'm getting 3 cosine x sine square x like this. Look at here. So actually we are using chain rule whenever we use power rule. Makes sense. Say something.
Good, sir.
Yes,
sir.
makes sense.
Yes, sir.
Good. Now, so as I told you, u to the power 7 du, now you have just one function in terms of u, everything is in terms of u. Use the power rule, u to the power 8 by 8, indefinite integral, your constant of integration must appear here. You have created for your convenience, u was not given here, so you have to go back and plug the value of u here. X cube minus 5 to the power 8 divided by 8 plus c is the answer. So actually this is just one step answer, but understanding is like this for the newcomer, for those who are learning this one first time. For the new learner, I would say. Okay. Clear? Now we change the function. Look at over here. X over square root of x plus 3 dx. X over, suppose I don't know about u or something like this. How can I integrate this function? Here it is x, here it is square root, even x plus 3. Very awkward function. I can't do anything. I can't take the integration. Because if you take x divided by x plus 2 to the power half in the denominator, that denominator square root function is bothering you. If you have square root function and numerator, you can think something to do with that function. But in the denominator, it will always bother you, always. So what I'm doing, if I take, and I told you that here it is x plus 3. If I consider x plus 3, I have to have one less power over here. But I don't have any kind of thing over here too. Right? So don't get confused, please. It says that x plus 3, if I consider, see how I'm converting this function. If I take, suppose x plus 3 equal to u. X plus 3, that means this denominator is u to the power half. Agree? U to the power half. But I have x over here too. If you convert this one in terms of u, you have to have everything in terms of u. You cannot write one term in terms of x and second term in terms of u. No, you are integrating just one time, means you are allowed to integrate your function either with respect to x or u, not simultaneously both. It's a different thing. Double integration, that's a different thing. Just forget it. But here, you cannot do that thing. So u to the power half. Because I want to remove this x, I want to replace this x by some u. So what can I do? U equal to x plus 3, linear function. So x equal to, send 3 to the other side, u minus 3. So if I take derivative of x, that is du, constant is 0. So dx is du, and this x is u minus 3. Everything that is in terms of u. Agree? Agree?
Yes, sir.
Yes, sir.
Yeah.
Sure.
Now you can see I have a bigger function in the numerator. The denominator is just simple root u, 1 u to the power 1 by 2. If I have u to the power 1 by 2 minus 1 or like this, you cannot go for term by term integration. But I have just one function. That means I can say, suppose a minus b divided by c means a divided by c minus b divided by c. Because single function is there in the denominator. And u to the power 1 and 1 by 2. So you can write u to the power is 1, base is same, quotient is there. So you can subtract the power. So 1 minus half is half. U to the power 1 by 2 in the denominator, in the numerator is negative half. Now you can use the power rule. So u to the power 3 by 2 by 3 by 2. 3 constant, pull it out. U to the power negative 1 by 2 plus 1. So u to the power 1 by 2 divided by 1 by 2 plus c. Replace your u by x plus 3. So x plus 3. This 3 by 2 in the denominator, here you can write 2 by 3. Right? A over b over c is a over b over c, that is equal to a times c by b. So 2 by 3 minus 3 and 2 is 6. U is this one plus c. Agree? Good. Next is e to the power root x over root x dx. If you consider root x equal to u, so it is e to the power u, e to the power u. But derivative of root x is 1 over 2 root x, right? 1 over 2 root x dx. I don't have 2 over here, that's fine. I told you you can play with a constant. Just send this 2 to the other side, multiply both the sides by 2. So it is 1 over root x dx equal to 2 du. I have one, look at this one, my pen. 1 over root x and dx is 2 times du. 2 is constant, pull it out. So pull it out and du. And now you can go for the integration. E to the power u is e to the power u plus c. U was root x plus c and done. Agree?
Yes, sir.
Good. Next is, all these problems are from your practice test. I'm going to provide you that thing too today. X cubed minus x divided by root x. Again, just like this example, x cubed minus x. So x cubed divided by root x and x divided by root x. X cubed minus 1 by 2. X to the power 1 minus 1 by 2. X cubed minus 1 by 2 is 5 by 2. 5 by 2. And x to the power 1 minus 1 by 2 is 1 by 2. Just use power rule and you are done. Agree? One more example. Don't look at this part, please. Just here. A, B, C, D, E, F. Sine square x and cosine x dx. You know derivative of sine x is cosine x. Agree? I told you that once you consider your u sub, you have to have the derivative of that function as a multiplier. So we have that thing over here. So sine x equal to u, cosine x dx equal to du. Just plug the values, u square and du. Derivative u cube by 3, sine cube by 3 plus c. But you can do, every time you are not supposed to just use u sub. You can, but sometimes formula help us. Formula helps us a lot. This sine square x, shall I write this sine square x is sine x to the power 2, sine x and whole to the power 2? Yes or no? Like this, sine x and whole to the power 2. Cosine x as it is and dx as it is. If I consider sine x as my fx, my function, and its derivative cosine x as f dash x. And this power, in general, I would like to write n. So this formula, whenever you have a function with some power and its derivative appears as a multiplier, in that case, you can just increase this power by 1 and divide by that number. So same function, increase the power by 1 and divide by that number. Fx to the power n plus 1 divided by n plus 1 plus c. So sine square x, sine cube x by 3 plus c. That's it. See? So I don't have to use a u sub and like this. Sine x, derivative is cosine x, increase the power by 1, sine cube x by 3. That's it. So whenever you will be having good command over this chapter, in future in DiffyQ course or Calc 3 like this, at that time you will be using this formula and you can get the answer, because you will be getting this type of terms in the middle of the example. So if you try to plug u sub every time in the middle of the examples, you are getting far away from your example and sometimes more chances to make some mistakes. So don't do this thing. Sometimes using formula is a better idea. To use the formula is a better idea. Make sense? Same here. So I'm just taking the various type of examples over here. If I take secant square 4 minus x dx. So 4 minus x is your u secant square u, right? And dx is just negative of du, negative outside. Secant square integration is tangent x, because tangent x derivative is secant square. So integration is the reverse process, plus c. and you replace your u by 4 minus x. Simple. Again, I have solved this example. See, in the book, you cannot find this thing that one example is solved by 2 different ways, 3 different ways. Okay, so that's why we are learning this thing. So tan square x and secant square x. Tan square x and secant square x. So u equal to tan x. Why I take u equal to tan x? Because derivative of tan x is secant square x. Secant square x. So du equal to secant square x. So u square du, u cube by 3, tan cube x, and c. Or if you take tan x and whole square and secant x. So this is my function fx, is derivative f dash x and power n equal to 2. So increase this n equal to 2 by 1. That means 2 plus 1 is 3. Same thing, same answer. Agree? So that's what we discuss about the u sub. One more example, question number 2D from your practice test. I will give you the practice test. E to the 3 to the power 3x dx. So 3x equal to u, 3dx equal to du, right? Consider 3x equal to u. Why 3x equal to u? Because you know a to the power x derivative is a to the power x ln of a. And a to the power x integration is a to the power x divided by ln of a, right? So that's why 3 to the power u, this formula is given on the first page, bottom part, right side, okay, in the formula sheet. So e to the power u du, e to the power u integration is e to the power u, 3 to the power u ln 3, u is replaced by your 3x, so 3x. This 1 by 3, if you can leave this example, if you want to stop over here, I don't mind. Otherwise, 3 to the power 3x minus 1 and ln 3. 3x minus 1 and ln 3 plus c. That's it. Now I'm taking really, really important examples. Look at here. Ln square x divided by x dx. Ln square x is, I can write ln x whole square divided by x. You know derivative of ln x is 1 over x, see? So the same function I would like to visualize this like this. Look at here. I have ln of x square divided by x dx can be visualized as ln of x square times 1 over x dx. Agree? Oops. Like this. Agree? Yes or no?
Yes, sir.
Yes, sir.
Right? So this is my fx. This is my fx. 2 equal to 2 is your n, and derivative of ln x is f dash x 1 over x and dx. So again I can take the formula. I can use the formula like this. So that is equal to, directly I can say ln of x cubed by 3 plus c. Just increase the power. Agree? Right? Or you can go for ln x equal to u like this. Ln x equal to whatever I explained to you, ln x equal to u. Right? You can go whatever you can see on the screen. But I would take like this. I would do like this. Ln x and the integration, so ln x cubed divided by 3. I'm getting straightforward, I'm getting the answer. Now let me increase the power. Instead of 2, let me take 3. Ln of x cubed. I'm sorry. It is ln square x. So that's why I wrote it down ln x whole square. But now it is not ln square x. It is ln of x cubed. This is a different function. You may get this type of function in your exam. You will be dealing with this type of function so many times in DPQ. Yes, mainly linear differential equation, non-linear differential equation. So many times you will be dealing this type of function, ln of x cubed. Mainly for the integrating factor for the linear differential equation. Yep. Anyway, so ln of x cubed divided by x dx. Now, before you proceed further, you have to use the ln property over here. ln property is ln of a to the power b is always you can take your power as a coefficient, b times ln of a. So here ln of x cubed can be written as 3 times ln of x. 3 you can take it out because the constant, take it out. 3 times ln of x by x. So 3 is out. I have just ln x over x. Ln x over x. Ln x is my fx. Its derivative is 1 over x. So ln x is u. 1 over x dx is du. U sub will give you 3 times it is ln x is u. 1 over x dx is du. So du. Answer. Right? Answer. Are you getting me, guys? So whenever suppose I ln x to the power 3, it is ln x to the power 5, 7, 10. First use this formula. Without simplification, don't go for the integration. Don't go for the use of.
Sir, is that on our formula sheet?
This formula? I think,
Yes, sir.
I think so. Just double check. I think so. It is there, but this is the formula from pre-calc. So, but I think it is there. If it is not, just memorize it. See, again, I'm going to take different ln. See, 1 over x ln x square dx. If you consider like this, 1 over x ln x square dx. Again, I have ln, it's not ln square, it is ln of x square, ln a to the power b. First use the logarithmic rule, ln rule. So it is 2 times ln of x, 2 times ln x. Take this 2 out, constant. So 1 by 2, 1 over x ln x. Now, there are 2 ways. One is you can consider ln x equal to u, and this 1 over x and dx is your du, like this. Or if you can, if you are more precise, or if you want to write it down more precisely, you can write this 1 over x separately over here, 1 over x over ln x. If you go for ln x equal to u, ln x equal to u, 1 over x dx is du. So this is your du. So it is 1 over u du, 1 by 2 ln u plus c, 1 by 2 ln of u was ln x. So ln of x plus c, ln x plus c. Right? Look at the answer. So what will happen if I take over here 3? What will happen if I take over here 3? 1 over x ln x cubed dx. So that means here it is 3 times ln x. So 3 times ln x. This 3, 1/3 will be out. Inside the function as it is, 1/3 will be out. Only thing is here it will be 1/3. Agree? 1/3 ln of ln x. Agree? Just 1/3. If
Yes.
I take 4 here, 1/4. If I take 5 here, 1/5. Right? Number of ln examples to get here. Are you getting me?
Yes, sir.
Good. What will happen if I take, look at here now. Let me go back. Let me go back slightly. No, I think I would like to stay with the same example. What will happen if I take ln times ln square x? Before I do this thing, I would like to let you know, let me just go back to this example and I would like to let you know one more thing. Here I have 1 over ln x and dx and I wrote it down like this, right? I would like to provide you one more formula for this example H, this part. Whenever you have, right now I have 1 by 2 integration 1 over x divided by ln of x and dx. And I used ln x equal to u. That's fine. But without that, you can use another formula. Let me give you that formula too. If you have one function in the denominator and its derivative appears in the numerator, in that case, you can go for ln of fx dx like this. So write down this formula in your separate piece of paper. Separate piece of paper. Okay? Yes or no?
1 second, sir.
Yes, sir.
Thank you, sir.
Okay. Now here the same function, right? 1 by 2 is just constant. My ln x, this my ln x is my fx. And 1 over x is a derivative, f dash x. Agree? F dash x. So it is ln x, that is my fx, and 1 over x, that is my f dash x and dx. Like this, just for understanding. Agree?
Yes, sir.
Yes, sir.
Okay. And this formula, whatever I give it to you, it says that you have to take the ln of your function. Function is in the denominator. So ln of your denominator function. ln of your function. So my denominator is ln x. So ln of absolute value of ln x plus c. See, directly I'm getting the answer. ln of ln x plus c. Agree? Agree?
Right.
Yes, sir.
Yes, sir.
Good. Now my question is, I gave you this one over, this is integration 1 over x times ln x square form, okay? ln x square form. But suppose I change my example, and if I give you 1 over x times ln square of x square form, then what will happen? ln square of x square form. Okay, first of all, shall I write this one as integration 1 over x times ln of x square and whole square dx? As I told you, always you can think like this. Agree?
Yes, sir.
Right. Now, first of all, use the ln property. So that is equal to 1 over x and 2 times ln of x and whole square and dx. Shall I say like this? Yes or no?
Yes, sir.
Okay. Now 2 is constant, but I have a square, so 1 by 4 is constant. So let me just pull this out, 1 by 4 and integration 1 over x times ln x square and dx. ln x square and dx. Agree?
Yes, sir.
Now if you use u equal to ln x, or you can use the formula, your choice. So du equal to 1 over x dx. Means I am getting 1 by 4 integration, u is ln x. So 1 over u square and du equal to 1 over x dx is du. So that is now power rule, u to the power negative half and du. So 1 by 4 u to the power 1 by 2 and 1 by 2 plus c. And that is equal to 8. U was ln x to the power half or square root plus c. It is 1/4 and 2, so it is 1 by 2. So you are getting something like this. Am I right? Yes or no?
Yes, sir.
Yes, sir.
Yes.
Right. I will take the picture of this page and send it to whom? I forgot. What is the name?
Me, sir.
What is your name?
John.
John Marcel, right?
Yes, sir.
Yeah. So let me take the picture and send it to you right now. VMI, JOHN, John Marcel. So you can play with different types of ln, right? Here it is just 1 by 3. So I think this answer is wrong. It is 1 by 3 ln of ln x plus c, not ln of ln x, please. Right? Because x cube is 3. Yeah, it's not ln of ln x. Yep. So this is just ln of ln x. Okay. Remove this ln, please. Can I remove it right now from here? Where is the pen? I was using this thing, but I forgot. Is it this one? I had an eraser and everything, but I don't know where it is. You have any idea, guys? Where is the eraser? This is.
Even if you had the eraser, it wouldn't erase like the ink you have on the document.
Okay, remove this ln. Okay. Okay, guys. What you said? Somebody said something. I want the eraser. Where is the eraser? You know, here. Oops, why this one is there? Delete.
Sir, even if you had the eraser, it wouldn't erase like the actual ink on the document.
Okay. Document. Oops. Okay, let's continue right now. I need to work on it. Is it here? Okay. Anyway, let's go for the next technique. Suppose I give you this example. This one. X cube plus 3x plus 1 divided by x. In this example, you can do like this. X squared divided by x, 3x divided by x, and 1 over x. You can do like that. Yes, of course. And you can go for term by term integration. But suppose you have x cube plus 3x plus 1 divided by x plus 1. I think I need to change this example. This is x plus 1. If you have x plus 1, you cannot divide term by term, x squared by x plus 1. It won't give you anything. So keep in mind this thing, whenever power of numerator, highest power of numerator is greater than or even equal than denominator, always go for long division method. And that's what I wrote it down. Always go for long division method. When power of numerator is greater than or equal to the denominator, long division. As I told you, you can, for this particular example, yes, you can do like this, term by term integration, you can get the answer. But if you have instead of x, suppose you have x plus 1, x plus 2, x plus 3, x squared plus 2. So if you divide by x, you know how to divide this one, right? Here it is x, highest power is 2. So let me multiply, well, let me write multiply by 1 more x, so that I will be having x squared. So here it is x squared. Change the sign. So this will get cancelled out. Then after, what is left out? 3x plus 1. I am having x over here. I have 3x plus 1. So let me multiply it by plus 3. So plus 3x. So plus 3x. Change the sign. This will get cancelled out. So I'm getting 1 over here as a remainder. Right? So this can be written as x plus 3, my quotient, plus remainder 1 divided by this one. So x plus 3 plus sign 1 divided by this one. You know LCM. If you take the LCM of this part, you're going to get this one. So long division divides your function, whatever you are taking before, LCM. So you can say reverse process of LCM. After LCM, you're getting this one, common denominator. But if you want to separate it out in terms of some plus or minus, that is the long division. So, well, I would say very rough sense, long division is a reverse process of least common multiplier or divisor. Because see here, and that helps us to reduce the power. It's x squared plus 3x. So I can write like this, and now I can go for term by term integration. Look at here. So it was hard over here, but now it is very easy and constant. So for this example, as I told you, yes, x is there, but look at the example number 2. Suppose you have x plus 1. Now you don't have any other choice. You cannot divide x cubed by x plus 1. Doesn't make sense. 1 over x plus 1, that makes sense, but x cubed over x plus 1, no. Again, because x cubed over x plus 1, highest power is 3 in the numerator. Denominator is just 1. So won't work. So if you do like this, x cubed minus 1 divided by x plus 1, you know this method, right? Long division, guys? Yes or no?
Yes.
Okay,
Yes,
so this
sir.
long division gives us like this. So let me directly write it down. The quotient x square minus x plus 1 plus remainder negative 2 divided by this one. Negative 2 divided by this one. And now nothing is there in denominator. So I can go for term by term integration. X cubed by 3 minus x square by 2 plus x minus 2 constant. Let me pull it out. Integration of 1 over x plus 1 is ln of x plus 1. Again, guys, people are making lots of mistake over here too. Look at here. As for example, what? Suppose I gave you this formula. Integration f dash x over fx dx is ln of fx plus c. Agree? Yes or no? Yes or no?
Yes, sir.
Right? Now, so many times people are getting confused. Suppose I want the integration 1 over x dx. 1 over x dx. What is the integration of 1 over x dx? What is the integration of 1 over x dx? What is derivative of ln x?
Natural log of x.
So what is integration of natural 1 over x?
ln of x.
ln x.
Ln of x, right? So that is equal to ln of absolute value of x plus c. But why? My question is, why integration of 1 over x is ln of absolute value of x plus c? Why? If you apply the same formula here, this formula. What is my fx? What is my fx? If you apply the same formula, what is my fx?
X, sir.
X, right? What is derivative of x?
1.
1. Can you see derivative of x 1 appears in the numerator? Yes or no?
Yes.
In the denominator, and derivative x appears in the numerator. And that's why I can use this formula, and I'm going to get ln of absolute value of fx. fx is x plus c. Make sense?
Makes sense.
Yes, sir.
Right? So don't think that you can use ln function blindly everywhere. No. You have to have the derivative of your denominator in the numerator. Only then you can use ln function. Another trick. You won't find this thing in the book, this type of explanation. But whenever you want the integration of some function in terms of ln, make sure you have to have your function in the denominator and its derivative must appear in the numerator to get or to use ln function. One more example. Suppose I give you integration 1 over x square dx, and numerator it is what? 1 over x square plus 1, right? Let me write. And numerator it is x. 1 over x square plus 1. Look at here. Can you see this page, this function? Where is it? Yeah, this one. My finger. Can you see this one? Will you please let me know the derivative? You can use x square plus 1 equal to u. That's fine. Because 2x dx equal to du, power is 1 less as a multiplier or divide or as a division. So you can use u sub. But you can use this formula too, because x square plus 1 is my denominator. What is derivative of x square plus 1?
2x.
2x. I don't have 2x. I have simply x over here. But as I told you, you can play with the constant. So you divide and multiply it by 2. You divide and multiply it by 2. Agree? Agree?
Yes, sir.
Yes, sir.
Now you have your denominator is x square plus 1. Its derivative is 2x appears in the numerator. And that's why I can write ln of x square plus 1 plus c. ln of x square plus 1 plus c. Agree?
Yes, sir.
X square plus 1 plus c. Right, guys? So don't use ln blindly. So here it is x plus 1, integration of x plus 1. Its derivative is simply 1 because x plus 1 derivative is 1, and that's why I'm using ln of x plus 1 plus c. Same thing, 1 over x square minus 9 dx. So 1 over x square minus 9 is 3 square dx. Your formula on the first page is 1 over a secant inverse absolute value of x by a plus c. Your a is 3. So 1 over a is 1 by 3. A is 3. Secant inverse absolute value of x by 3 plus c. Just use the formula. 7 over x square plus 7. Just pull this 7 out. You are getting 1 over x 1. This is 1. 1 over x square plus root 7 square. If you compare with the formula 1 over x square plus a square, integration first page again, it is 1 over a tangent inverse x by a plus c. So 1 over a is root 7, tangent inverse x by a is root 7 plus c. 7 common, just simplify this one. Question 7, again in your formula sheet, from your practice test, is important. Question 7. 1 over x square minus 2x plus 8 dx. See here, how can you get the integration of this function? It's not that easy. It is easy, of course, but whenever you have some function like this, mainly quadratic function in the denominator, always try to make that function as a perfect square. Perfect square, x square minus 2x plus 1 is a perfect, the perfect square of this function is x minus 1 whole square. Agree? Already I have used 1 here to make this one as a perfect square. So what is left out? 7 is left out. Agree? 7 plus 1 is 8. So 8. Does it make sense?
Yes.
Makes
Yes,
sense?
sir.
Yes, sir.
Okay. Okay. So now 1 over x minus 1 whole square and root 7 whole square. Root 7 whole square. Again, it is of the form 1 over x square plus a square dx. Just like previous one, 1 over x square plus a square. Formula. 1 over x square plus a square is 1 over a tangent inverse x by a. Or you can write u equal to x minus a, and then you use the formula. Same thing. So tangent inverse x by a. Tangent inverse x is x minus 1. X minus 1 by a is root 7. So again, formula. People are getting confused for example number 8. Then 10, 11, 12, 13. I think lots of things are there. So, okay. And that is the end of this part. Yes, this is number of problems are there. This is 6.1 integration by 6.2. I think you are taking your exam on Tuesday. So if you want, we can stop over here and we can continue from this example next time onwards, because I don't want to give you all the techniques, all these things at a time, because I just want you to focus on your exam first, right? So let me stop over here with example number 7 and example 8 onwards. Just remind me, okay? If I forget on Tuesday, just remind me. Tuesday, you are taking your exam, right? Ooh.
Yes, sir. Sir, do you want me to message you the number so that you remember where we are?
Number means, let me write it down over here. So page number 15, example 8, right? So you want me to stop over here, but you are taking your exam on Tuesday. So do what? I think that sounds good, no problem. Okay. Or let's go for one more example, one or two more examples, and then we stop, okay?
Yes, sir.
Okay.
That works, yes, sir.
Yeah, let me take this example. See, look at over here. 3 over negative of x squared plus 8x plus 9. Looks very awkward example. What I'm going to do, let me work with this denominator first. So negative x squared plus 8x plus 9 means I can write 9 minus is common, x squared minus 8x, right? Let me make this one as a perfect square. Why? Because I have a formula 1 over a square minus x square. This is the formula. 1 over a square minus x square is sine inverse x by a plus c. Arc sine x by a plus c. Because I have a constant at the first level. So a is a constant. And 3 square is 9. So this formula is the best fit for this type of example. Only practice will make you perfect. So you don't think that I am using this thing. No. If you solve 100 examples, you will get the grade. So 9 minus 8x minus x squared plus 16 and minus 16 so that I can make a perfect square over here. So if I add and subtract 16, so this is x minus 4 whole square. This minus and minus is plus, so plus 16 is out. 9 plus 16 is 25 minus x minus 4 whole square. So this function can be written down in the form of 25 minus 4x minus 4 whole square. So it is now a square minus x square form exactly. Look at here. Or you can write x minus 4 equal to u. Same thing, or directly. So that is equal to sine inverse of, see, that is equal to sine inverse x by a. So sine inverse x is x minus 4 by a is 5 plus c. Because this a square is 25, so a is 5. So like this. Okay, guys?
Yes, sir.
Good. Then let me take this example. Example number 11 may give you little pain. Little bit. It's not that hard, but look at here. X cubed minus x and x squared plus 4x plus 9. Again, power of numerator is higher than power of denominator long division. If you take this long division process, you are going to get quotient x minus 4 remainder 6x plus 36 and this one. So x minus 4 plus remainder divided by this part. So divided by this one. And now you can say that power of numerator is less than power of denominator. So I'm good to work over here. This is in simple x term by term integration x squared by 2 minus 4x. Here, let me take, see, look at here, just try to focus denominator. Try to focus at the denominator first. What is the derivative of x squared plus 4x plus 9? It is 2x plus 4, agree?
Yes, sir.
2x,
Yes, sir.
not simply x. I want 2x plus 4. 2x plus 4. And what I have over here? 6x. So I want 2x over here. So I'm not taking this my 6 out. Of course, you can take 6 out. That's 6 here and 36 here, so 6 out. But I don't want to take 6 out. I want 2x here because derivative of denominator is that is in terms of 2x. 2x plus 4. So let me take just 3 out. So 2x is already there over here. 2x. If you take 3 out, so here 2x and here it is 2. Agree? 3 2s are 6. But again, derivative of denominator is x squared plus 4 or 2x plus 4. I have 2x plus 2. I want 2x plus 4. So let me add here 2x plus 4. Look at here. What is this? I think I made a mistake. Yeah, it's not 2, it's 12. This is 12. Because if you take 3 out, here it is 2x and here it is 12. Right? But out of this 12, I want just 4 over here because derivative is just 2x plus 4. So I don't want 12 here. I just want 4. So let me take 4 outside, 4 separately, and then 8. So 2x plus 4 plus 8. Agree?
Yes, sir.
Okay. So what will happen now? Let me separate these two functions. This divided by this one and this divided by this one. Yes. Because this divided by this one, my function's derivative appears over here in the numerator. I can use ln function. So 2x plus 1 x square plus 4x plus 9 derivative is 2x plus 4 appears over here in the numerator. Ln of x square plus 4x plus 9 is the integration of this part. First part is already done. Only thing is I need to take care of my last part. 8 divided by x square plus 4x plus 9. 8. But actually it's not 8. It's 8 multiplied by 3. So it's 24. So let me pull this 24 out and 1 over x square plus 4x plus 9. So I'm done with my first integral. I'm done with my second integral. Only thing I'm taking care of my last integral. See, this is 1 over u and ln of u, blah, blah, blah. So 24. 1 over x square plus 4x plus 9. Again, this example is type 8 or 7, tangent inverse form. Because I can make a perfect square here. X square plus 4x plus 4 and plus 5. 4 plus 5 is 9. This is x plus 2 whole square plus root 5 square. So 1 over a square, x square plus a square. And that will provide you 24 out. 1 over a tangent inverse x by a. Tangent inverse arctangent of x is x plus 2 by a is root 5 plus c. Make sense? So sometimes you have to be very careful or you have to play with your function, right? And try to set up your example, your different terms of the example in terms of your standard given formula and apply those formula correctly and get the answer. Agree?
Yes, sir.
Okay. And I think other examples, they are just quite simple. So you can go through these other examples. And that is the almost end of this 6.1. So let me finish this example and then we'll stop. Rest of the examples you can just read. Number of things are there in front of you. So just read this example. So this is 3x plus 5x square minus 2x minus 6. Again, let me work with the denominator. X square minus 2x minus 6 is that derivative is 2x minus 2 dx. 2x minus 2. I have 3. I don't have 2. Right? What I'm going to do first, let me write it down separately. 3x over square root of this one plus 5 and square root of this one. So naturally, this is 5 and square root of x square, something like this. So that will give you 1 over x square minus a square form. But square root sign is there. It's not, tangent inverse will not work because square root sign is there. Another thing is you're going to get something in terms of minus. So arctangent will not work over here, but something different, some different formula will work here. Here, 3x over x square minus 2x minus 6. Derivative of x square minus 2x minus 6 is 2x minus 2. 2x minus 2, right? Let me take this 3 out. 3 out. I have just x over here in the numerator because I took my 3 out. Derivative is 2x minus 2. I have x, but I want 2x. Let me divide and multiply by 2. Divide and multiply by 2. So I'm getting 2x now. But I want 2x, not just 2x, I want 2x minus 2. Are you getting me, guys? I want 2x minus 2. I'm getting just taking 3 out and dividing and multiplying by 2. I'm getting 3 by 2 here, and here it is 2x. Here it is 2x. But I want some additional factor because if there is 2, how can I write 2? If you write 2 here, that means negative 2 because it's a derivative, negative 2. So actually you are not writing 2 here. You are multiplying this by 3 by 2. So 2 and 2 will get cancelled out and 3 is there. So actually you are writing negative 3 here. Negative 3 here. Because you are writing negative 3, you have to add positive 3. So this 5 and this positive 3 is 8. That's why this part is 8. All of you are getting me. It's little tricky. Right? I repeat, this is my denominator. If I want to consider this one as my u, derivative of u is 2x minus 2. Because I have just x over here, I can pull my 3 out and I can divide and multiply it by 2. So I'm getting 2x, just derivative of first term. But still I'm looking for minus 2. So I have to have minus 2 over here. If I write minus 2, I have to write plus 2 over here too. I think that's the best way of writing minus 2 and plus 2. This minus 2 that means it's a derivative of denominator. And plus 2, if you write plus 2 and if you try to multiply it by 3 by 2, 2 and 2 will get cancelled out and 3 is left out. 3 is left out. So 3 divided by this one, just like 5 divided by this one. So add this 3 and 5 and merge this 3 with this 5 and you are getting 8. Now things are easy. This is your derivative u and its function and its derivative here. So u to the power negative half, right? U to the power negative half is denominator, so numerator is negative half. 8, make a perfect square here. X square minus 2x minus 6. So if you write x square minus 2x plus 7 plus 1 minus 7, so it is minus 6. But this is a perfect square. X minus 1 square minus root 7 square. And this derivative, this integration is again standard formula. Integration of 1 over square root of a x square minus a square is ln of x minus a plus square root of x minus a square minus plus square root of x square minus a square. I think this formula, I don't know whether it is there in the formula sheet, but let me write it down for you guys. One formula is like this. Integration 1 over square root of x square minus a square dx is equal to ln of absolute value of x plus square root of x square minus a square, absolute values over plus c. This is the formula, the star formula. Look at here, I put the star here. Just write down this formula. Done. Done.
Yes, sir.
So 1 over x square minus a square dx square root is ln of x plus square root of x square minus a square dx. If you want, let me, John, do one thing. Don't send that previous page to these guys. Just send this page to all the guys, okay? Because this
Yes, sir.
is all the formulas. I think it will be better for all of you. Yeah, you will get it. Okay, guys, and rest of the form examples. Look at over here. This is one of the examples with definite integral. Range is 2 to 6. You know how to solve definite integral. X minus 2 is your u. Then use definite integral. And you can get like this. Just go through this example, each and every step. I solved this example by 2 different ways. See here, I have used x minus 2 equal to u. And like this, and then after I have used like this. So definite integral, you can plug the range and make sure both ways you are getting the same answer, 352 by 15. So please read this example. This is another example, x square plus 2x plus 1. Derivative of x square plus 2x plus 1 is 2x plus 2. 2x plus 2. So if you write 2x plus 2 over here, 2 common, so it is x plus 1. So function is already there as a multiplier. Use of will easily work here. One more example which you can convert in terms of arctangent, because x square minus 6 is perfect square without square root sign. So you can convert this one in the form of x square plus a square form. Right? And I think, yeah, all these examples, please guys work hard, please. You have chosen to take your exam on Tuesday. So please spare some time if it is possible on this long weekend. Otherwise, work at least for 3-4 hours on Tuesday. Otherwise, you will be out of the track. And that is the end of article 6.1. I don't want to suppress you. This is one more example with separate formula. Yeah. These 2 examples are really good examples. So just please read these examples. try to convince yourself, because same technique. This is another formula I have used over here, which is given in your formula sheet. 1 over x, square root of x square minus a square is 1 over a secant inverse absolute value of x by a plus c. Yeah. And that is the end of this article 6.1. Okay. So now next time we will be starting with 6.2. So we don't have to remember anything now. So techniques of integration. That's article 6.1. Okay, guys, so let me stop over here. Do you have any doubt? Any doubt? Okay, good luck to you guys. And I will make sure to send you the example. I will put those examples on Canvas very soon that remind some examples. Okay.
Awesome. Thank you very much, sir.
Thank you, guys. Thank you so much.
Thank you.
Thank you, sir.
Yeah. Bye, guys. Take care. Have a good weekend.
Thank you, sir.